Let's check this paper, Decoder Hybrid Decoder Architecture for Efficient Reasoning with Long Generation. This paper introduces a new neural network architecture called Samba-Y, designed to be highly efficient, particularly for tasks that require generating long sequences of text, such as complex reasoning. The core innovation is a simple yet effective component called the gated memory unit, which allows different layers of the model to share information efficiently. By integrating GMUs into an existing efficient architecture, Yoko, the authors create Samba-Y, their largest model, 5 for mini flash reasoning, and this is by Microsoft, by the way, so they use their own 5 this paper demonstrates a superior performance on difficult reasoning benchmarks compared to a strong baseline 5 mini reasoning. Most importantly, it achieves this while being significantly faster, delivering up to 10 times higher throughput when generating long responses. The problem that they are solving is the cost of long generation. So you know that when LLMs are reasoning, they create a lot of tokens, and Transformer struggles. It has quadratic growth with the sequence length, number of tokens. And then linear models like state-space models and RNNs, they have linear scaling, but they omit a lot of information, lose a lot of information as the sequence grows. Hybrid architectures like Yoko improve efficiency by using a self-decoder with efficient layers like SSMs and one full attention layer. I actually have this kind of model that on my channel. It's called I trained my first LLM that speaks coherently, something like that. The KV cache for this single attention layer is then reused by all subsequent cross-attention layers in a cross-decoder. This makes processing the initial prompt fast, linear time. However, during the generation phase, every new token still requires all the cross-attention layers to read from the large KV cache, creating a memory input-output bottleneck. So every new token requires all of the cross-attention layers to read from the large KV cache, which creates a memory input-output bottleneck. The paper aims to solve this generation stage bottleneck, making reasoning with long chain of thoughts much more efficient. Core innovation, the gated memory unit, GMU. It's a mechanism for efficient memory sharing between layers. A GMU at a given layer L takes two inputs, the current hidden state X and the memory state M from previous layer L. It then uses the current state X to gate or control how the information from the memory M is used. How it works. The operation is a simple element-wise multiplication. Output is memory at, this is maybe element-wise multiplication, gate that passing in input through the gate, and then multiply with weights, which is the learnable matrix. The intuition. This allows the model to dynamically and selectively reuse representations from earlier layers. The current layer's input acts as a query that recalibrates the token mixing that happened in a previous layer, but in a much cheaper way than a full cross-attention operation. A bit tough to understand. The proposed architecture Samba-Y. Samba-Y is a novel decoder hybrid decoder architecture that applies the GMU to the Yoko framework. The architecture consists of self-decoder. This part processes the initial prompt. It uses Samba, an architecture that interleaves efficient Mamba (SSM) layers with sliding window attention. It contains only one full self-attention layer. So here we have Mamba, sliding window attention, Mamba, full attention. Then memory caching. After the prompt is processed, two things are cached. The KV cache from the single full attention layer, as in Yoko. The output state from the final Mamba SSM layer. This is a small, constant size memory piece. Cross decoder. This part generates the response token by token. Instead of using only cross attention layers like Yoko, Samba-Y replaces half of the expensive cross-attention layers with cheap GMU layers. The remaining cross-attention layers read from the large KV cache. The new GMU layers read from the small constant size SSM output state. So here you see after full attention we have this GMU cross-attention, GMU cross-attention. This design leads to significant efficiency gains. Prefill efficiency, like Yoko, processing the initial prompt has linear time complexity. Generation efficiency, during the coding, the memory input-output cost is drastically reduced because half the layers perform a constant time GMU operation instead of a linear time cross-attention operation. This leads to a massive speedup for long sequences. Half of the layers perform a constant time GMU operations instead of linear time cross-attention operation. Okay. Key experiments and results. The authors conducted extensive experiments to validate Samba-wise effectiveness, scaling behavior. To ensure fair comparisons, the researchers developed a principled method called MuP or microprocessor ++ for scaling hyperparameters. These experiments show that Samba-Y scales better than other architectures. It exhibited a lower irreducible loss, which suggests that as more computational resources are invested, Samba-Y's performance potential is higher than that of the baseline. It's very good on benchmarks that involve context retrieval, long context retrieval. Interestingly, here we have differential attention. This was the big thing, like the big paper, but this is the first time I'm actually seeing it in use. So benchmarks are good. I wouldn't trust benchmarks so much. Only time will tell. Time is the best benchmark. Conclusion: the paper successfully introduces the gated memory unit GMU as a powerful tool for efficient inner layer representation sharing. By creating the Samba-Y architecture, the authors present a model that excels at both performance and efficiency, particularly for reasoning tasks require long generation. That will be it for this video. Thank you for watching. Check out other videos on my channel and see you next time.